All right. Good morning, good afternoon, good evening, everyone. It's a pleasure to have today's speaker, Nick Murzin, who's going to talk to us about interpreting quantum probabilities. Now, Nick has been working on the physics project right since the beginning, since 5 years now, and he's been closely involved with lots of projects that Stephen Wolfram himself has been doing in the context of the physics project and even beyond. Nick has also is also a fellow of the Wolfram Institute, and Nick has been basically a programming wizard. Programming is his passion, and in a way, he can study any subject where there's programming involved, and he just learn it, master it, and come up with good tools in it. Before joining Wolfram, he was also working at IBM, and right now he's been doing lots of different topics in physics and mathematics. In the reading list, you may have a look at some of the recent community post computational essays that Nick has written. And I invite you to check some of his earlier writings from the last 1 or 2 years. You'll see some very interesting things that he's been doing. And do take the opportunity during the school to catch him and get some nuggets of insight. So thanks, Nick. Let's go ahead and have your talk.
Thanks, Xerxes, for this introduction. Quite unexpected, but okay. So, as a fair amount of warning for this talk, it's like I really don't know what I'm talking about. It's like you can see, it's like I have like 3 titles prepared already, because I wasn't really sure what it's going to be about. I just was sure that I have to want to talk about quantum computation and how the probabilities and amplitudes and Hilbert space can be interpreted more or less closer to a computational paradigm that we have within the Wolfram physics project. But starting from the more classical approach to quantum computation and quantum probabilities, like starting from Hilbert space and phase space and all that. And I was just like making a bunch of examples. I'm gonna use for this talk. I'm gonna heavily use our Wolfram quantum framework. Basically, that's the line that you can install the development version, because I have already, in preparation for this, I improved some of the functions there to make some presentations and like pictures a little bit better. So that's how you install the Packlet, the most latest version of it, directly from the cloud. That's how you load it, right? And basically, first I'm not gonna do some crash course on probability theory. I assume that you already know what classical probabilities is and how you can manipulate them using conditional probability tables and just what conditional probabilities is and things like that. I'm gonna like straight ahead start from conventional quantum states, right? And how you can construct them within this Wolfram quantum framework that we have, right? So conventionally, as many of you already know, quantum states is just some list of amplitudes, right? So that's a Dirac notation. You have some cats 0 and 1, and you usually there's some amplitude associated to each of those basis states, or eigenstates they're also called, right? So that there are quantum amplitudes depending on which state you construct. This is one of the states that contain the actual complex amplitude, but you can construct like a random one, or maybe just the basis state itself, which doesn't have any complex amplitude, which is just 3 or 1. So it's just a simple thing. And then you can like ask for usual Born rule, right? The Born rule basically means you have to take the squared amplitudes, modulus squared amplitudes, to extract the probabilities. And that represents your observable probabilities that you would observe by applying some type of observable to that state, right? Most of the examples, I'm going to use some random states, so that it's not like some particular one, like these nice ones with some exact amplitudes. I'm going to just generate a random state, which is just contains some random numbers, but it kind of helps to show all the in all generality. You can assume that this is like the most general state, the pure state that you can get, right? And just straight ahead introduce some way to represent these amplitudes in a different way than the conventional one as a state vector of complex amplitudes, right? The one this picture, which is just simply a property in our framework that you can ask for any quantum state, even probably I haven't even tried it. Probably you can ask for a 2-qubit state. This is how you generate a random 2-qubit state, pure one. And if you ask for a transition graph, it's going to generate a more complicated graph, right? But this graph which I call simply transition graph, simply shows some real numbers. So that's the main difference already, that it doesn't involve any complex numbers, even though this picture is completely analogous for any quantum states. You can generate this representation for any arbitrary qubit or qubit of multiple systems. So it doesn't rely on being two-dimensional or just a single system. Like, you can generate this graph for any quantum state, even mixed ones, right? But those numbers are just weights on the edges. So some already represent some kind of formal transitions. And you can see that in this particular default states are just computational, have two types of states. There's in computational basis, and it's Fourier dual, which is X basis for qubit. It's like if you, for example, if you plot this, if you show this particular state in the conventional block space, which is just an arrow pointing on some sphere on the block sphere, right? It just points on some particular position on the sphere, right? And you can see that there's a z-axis in that sphere is what we call a computational state, a computational basis, or just z basis, and the x basis is just one of the axes, which is usually which is the x-axis. So x-axis for a qubit serves as a Fourier dual for the z-axis. So they form. So that's why this particular transition graph already shows some kind of relationship between the Fourier dual and its Fourier dual variables, which is in this case is just z-axis and x-axis on the in the block space. But how was this graph was generated, right? Because yes, this is involves some positive and negative real numbers, right? You can even ask for. I guess I'm gonna show it later, right? It contains some. If I generate it again, it contains some. Its adjacency matrix is just some numbers, and this adjacency matrix is essentially what usually people call quasi-probabilities, right? It's a quasi-probabilistic representation of quantum states. So those are, you can think of them as probabilities, but because they have some negative numbers, they're not quite as probabilities in a classical sense, right? So this transition matrix shows that the sum of the transitions should be negative, but you still can recover some properties by marginalizing all these probabilities. For example, this table, if you just extract this table and sum over all of them, you can see that they're normalized to 1. So if you sum up all the numbers, you get 1. So they're normalized. And if you sum up just the rows, you get some probability vector back, which is always going to be guaranteed be always a normal probability vector with only positive values that sum up to 1, right? And if you sum up columns, you also get a normal classical probability vector. And those numbers would actually correspond to the probabilities of those born probabilities that you get by squaring the absolute value of amplitudes, right? So that's equivalent. So if you ask for probabilities of that state measuring the computational basis, that's exactly the same numbers here and here, right? That you just recover from summing over rows of this adjacency matrix in this graph. So in a way, this corresponds to some joint probability table for this state. So now, but it's not a probability table, it's like quasi-probability table because again of this funky minus sign, right? But you can recover all the probabilities of actually measuring that state in some basis by just summing over that table, right? And we have a conventional nice property in the framework. You can just ask for, maybe not for extracting from the graph, because it also contains some zero transitions because it involves four vertices, so it has to be 4 by 4. You can ask just for this particular subpart of this matrix that only represents the probabilities that we're interested in. So that's like a prime. Don't worry what prime means. It's some technical details. Maybe I can answer it later if someone asks. But that's basically the table that you can, the quasi-probabilistic table that you recover these numbers from. And what you can do immediately, you can ask yourself that, okay, if we can represent this probabilities as some kind of transition probabilities in this graph from state to states that form this Fourier dual, why not just invert the edges, right? Invert the edge, negative edge, and now you can have like a probability table which only contain positive numbers, right? So that now all the transitions are positive, and you can again represent the same state, because you can go back and forth. It's the equivalent mathematically representation for the state, but now with only positive numbers. But now probabilities should be recovered not as more generalizing over this adjacency matrix and all that, but some kind of flow through the vertex. So for example, like the same probability of measuring x plus here, which corresponds to this probability, you have to subtract the outgoing edge, weight of the outgoing edge from subtract the ingoing weight edge, basically. That's how we recover the probability. So it's kind of a flow or through this vertex. But one interpretation of this flow of probability through a vertex to get its actual observable probability, you can think of it as some kind of residence in time or computational time, right? I don't know. It's like some hand waving interpretation, but you can think of this number as okay, this system, the state itself, the quantum state itself, represents a dynamical system on its own, which is not a static thing that we usually think of quantum states. We don't even introduce any unitary evolution operators or Hamiltonians yet or measurements. We just have a static quantum state without any dynamics. But on its own, you can think of all those probabilities that it encodes as some kind of artifact of an underlying computational system going on, so that these weights in the transition graph correspond some kind of how the system, how much time the system resides in that transition, something like that, right? So this is like one of the interpretations that you can assign to any quantum state, just by but it's not clear how to like generalize it into when like new things would be introduced later, like what happens when you have multi-party systems and you actually have dynamics, how those weights going to be evolved. But this is one, but that's the starting point. Okay. But now I'm gonna so any questions at this point? Whether you can ask, interrupt me, like at any moment, like if something is not clear yet. Yeah. Yes, Eric.
Just my question is, when we are doing the when we adding the rows or the vectors of the adjacency matrix, how do you interpret the resulting vector when you add all the rows? Like it seems like when you add all the columns, but
Well, if you add this when you already invert the negative edge and turn them into positive, I don't think there's a nice interpretation for that.
no, I mean
When
before you flip, like even with the negative probabilities, what
when
should this
we
mean?
summed over these numbers, it sums up to 1, right? When we sum all the numbers, it sums up to 1. So it's kind of normalized. Even though this has some negative number, it's guaranteed that it has some positive bias. So it sums up to 1.
No, I meant like the next command when we get this vector, normalized vector, of summing all the rows or all the columns.
So this one.
Yeah.
Well, it's like a marginal probability, right? It's like usually when you have in classical probability theory for this finite dimensional state, if you have a joint probability, for example, you have 2 coins and they somehow correlated to each other, and you can represent it by a joint probability table, 2 by 2 joint probability table, so that you can say that there's a probability of observing head, tail, heads, tails, tails, right? You have 4 numbers. So, and then if you summing rows and columns basically means you're marginalizing over one of the coins, either second or first one, and you get the probability of what is the probability of measuring the first coin being heads or tails or the second one. So this is exactly the same, right? Those are marginal probabilities, but asking about these Fourier dual variables in 2 different eigenbases.
Okay, thank you.
So we haven't used the Born rule. We just directly extracted it from this matrix, right? Without any squaring of complex numbers. So kind of in a way, this is like complete. You can go back and forth. So it's not like some weird theory. It's just an interpretation, mathematical equivalent theory for quantum amplitude. So and density matrices. You can represent it by these adjacency matrices that contain quasi probabilities. That's basically what I'm saying. Okay. And in our framework, it's very easy to use. Okay, but what I want to talk about in more detail how those numbers actually computed. right? And they involve so-called phase space representation, right? It's usually like when people talk about phase space for quantum mechanics and quantum theory and quantum mechanics, they talk about Wigner distribution, Wigner quasi-distributions. Basically, the quantum mechanical system, especially they're heavily used in quantum optical systems when people construct these Wigner distributions for some optical systems, so that it's still a continuous system. So it's not very well explored, I would say, for just simple finite dimensional systems. So it's kind of surprising to me that it's like was surprising to decode how this representation work for a simple qubit, right? Even for a simple qubit, not for some quantum mechanical optical system. So basically, what we have, but we worked on it for a bit and actually figure out what is the best representation was and what is the best way of actually working with phase space for finite dimensional systems like this, right? There is just a special types of bases you have to know about. Like the Wooter's basis is a very convenient one. That's exactly what I've used for to construct this particular transition graph, right? That's a so essentially this command that turns our quantum state, our quantum random state, into phase space given some basis. That's exactly it's gonna make a quantum state, but it's gonna be amplitudes. All the amplitudes of that state is gonna be real, right? So that's what we usually mean by the quantum space, phase space of the quantum state. It's just a representation which has squared number of dimensions. So if in complex numbers it was 2 amplitudes, its phase space should be squared with that. So 2 squared is 4, so it has 4 amplitude of real amplitudes to represent that state in phase space, right? And the exact numbers the exact same numbers that we had in this transition graph. It's just the interpretation of those as weights requires some additional thinking, but there's like a multiple bases you can do. There's like this Wooter's one, which is a exact one. The default is just Wigner one, which is more common one, but it's like represents. It's a little bit different way of converting it, but they're all equivalent. And the fact that they're equivalent to original quantum state is that the fact that you can convert back and forth. And by the way, if you can also think of it as why there has to be 4 amplitudes or 4-dimensional quasi-probability vector, because quasi-probability is always normalized to 1. So it's in a way, even though there are 4 numbers, there are 3 degrees of freedom because of that normalization condition to 1. And the density matrix for a qubit, which is a Hermitian in the conventional quantum computational approach, the density matrix also has 3 degrees of freedom because it's Hermitian, right? And with trace 1 and all that. All those conditions exactly summarize the state, and so that it also has the same number of degrees of freedom. So those are representations equivalent, and you can go back and forth with this quantum phase space transform and the Weyl transform, as we call it. That's the inverse transformation. So that's the same table I showed above, which is the prime quasi-probability table, the part of the adjacency matrix of the transition graph, right? Now you can, so that you can also label the rows and columns by the corresponding eigenstates, or the basis that, and its Fourier dual, right? And this is like also again showing that you can recover the probabilities by summing over them. But in phase space, but in addition to that representation, when the actual amplitudes have some negative numbers, there's a possibility to construct a basis, a different basis for the phase space that always guaranteed to be a normal classical probability vector. So it means there is no negative numbers, just a probability vector, which also can be converted back by the Weyl transformation to the original density matrix representation, but all the numbers are positive. There are also multiple bases for that, but one of the popular ones, the most straightforward ones for qubit at least, which also has some nice geometrical interpretation. That's why it's called the tetrahedron one. Maybe I'll show it later. But basically, all you have to know at this point is just that that's one particular basis in phase space where any quantum state, pure one, mixed one, any qubit, in that particular basis is just a probability vector. So all those numbers are positive, right? And it's summed up, and it also normalized to 1. And there's some visualization you can use. That's what I call a sector chart. It also takes some bases, like for example, this Wooter's one, which contained the negative number. That's how we would represent a negative number in the sector chart visualization for the quantum state. But in the tetrahedron one, it's always going to be positive. So it's just all of those 4 numbers is just the thickness of that sector is represented by this number, right? And what you can do is essentially have this. There's an additional type of transformation you can do, which I'm going to talk about in more detail later, when you just represent an additional, all those states as an additional basis state in that phase space representation. And you also represent a new one, but with the negative sign. So that's what you can, that's why it's called a positive transformation, because it transforms any phase space representation into positive one, even those that have negative numbers. So even though, even like this one, this state, for example, in the Wooters basis, our state had a negative probability, right? In the positive transformation, we just turn this negative probability around and just call it a different state, right? We just assign it a different label, right? And that's how you can also visualize these labels. It's just the same kind of sectors, but they have 2 different signs, positive and negative. Okay, so this is a and again, and in the tetrahedron, it's always going to be positive. But those are okay. I can any questions at this point? Because now we're going to go to processes. Okay. So this was just a simple representation for quantum states, but it's not a very interesting on its own, because we have to know how we can represent dynamics. So we have to represent how would in that picture the processes would look like. Processes are like unitary gates, unitary transformations, Hamiltonians, measurements, any kind of quantum channels, and noise, right? All of those are just examples of quantum processes. Like in the circuit diagram, you can just think of it as, okay, we have a quantum state. We already know how to represent it using some quasi-probabilistic, semi-probabilistic approaches above, right? But now we have to know about how we represent a process. What does the quantum process is doing to that quantum state, right? For example, this is just a like Hadamard gate, the simplest example of a quantum process you can imagine, I guess, right? And you can also transform it into the same representations that we just talked about, applicable to a quantum state. Now they're also applicable to any quantum process or quantum operator in this case. So we have if you have a Hadamard gate in the same kind of phase space, which is always positive basis, which is our tetrahedron basis, it's just some particular conditional probability table, you would say, but this conditional probability table is not the conventional classical one, because now, even though we're using a positive basis, which like in which basis any state looked positive, now the process always gonna contain, or at least most of the time, most of the process is gonna contain negative probability numbers. So the conditional, so the problem lies not in the state, but in the actual processes and how those states are being manipulated, because there is no clear way to get rid of these negative numbers. So now it's like the same kind of thing. And just to show more concrete examples, again, choosing some random unitary, right? Some random unitary can again contain some negative numbers, but you still have the same kind of normalization applied. So if you extract the matrix and ask for like summing over columns, right, or sum over the rows, you see that they all sum up to 1. So in a way, they behave exactly like any conditional probability table for like classical stochastic processes would behave. So they normalize to 1 so that you can use this table to resample your random variables or whatever. But the only difference is that the entries in that matrix contains negative probabilities. So you can't really think of them as a stochastic processes that resample some random variables anymore. So we have to come up with some better interpretations, what those negative probabilities actually mean. So, but now at least we know, and you can do it for any quantum process. Here it was a unitary transformation, right? Just a unitary gate. You can apply the same thing for measurement, right? So just an example of measurement, right? And have to do a little the measurement. The measurement, we usually think of measurement as the same quantum process, just reducing the dimensionality. It's kind of deliberately throwing away some information. Like maybe there's some device coupled to a system. We correlated the device and then throw away the system so that we only pick only leave the actual readings from the device, right? So that's how measurement works under the hood of any quantum system. But we have to, instead of phase space transformation, we have to do a little bit trick of just directly converting some measure operator that we have, which is like 4 to 2, this direct transition, which is like a decoherence operator. It just leaves the diagonal elements of a density matrix. You can think of it this way, right? It just throws away off diagonal elements, and you convert it directly to this tetrahedron and output as a computational basis, right? And it looks like a conditional probability table again, but with a negative number, right? But it's not a bistochastic. It's like the columns sum up to 1. So like obviously this is 1, this is 1, and this is 1. But even though this is 1, it contains a negative probability table. So it's a stochastic matrix, but it's a quasi-stochastic. And you can like apply the same kind of transformation for any quantum process. And that's how mathematically, at least, you operate with probability vectors that represent states using this representation for quantum processes. All right. Okay. Any questions? Now we're gonna explain it in a little bit different way. Okay. I don't know. So we have so you probably heard about the Feynman integral formulation for quantum mechanics and all that, and quantum field theory and things like that. But in this finite dimensional Hilbert spaces, it's much more easier to think what those Feynman path summation in this case, because we don't have to integrate over anything. It's like everything is finite, so just a simple sum. So how can we represent our quantum states by just summing over paths? Well, when we have a quantum state, you don't really have any paths. You don't have any dynamics yet. But you can start thinking about, okay, if you make a circuit that contains only our initial state, right? What those original amplitudes, you can just label them all the edges in the path. So now, in a way, to recover the amplitude for the state, you just sum over all the paths, which is this like the simplest case possible. The path only contains a single possible path in each destination of our eigenstates. So those how would you compute the path sum without any dynamics? Pretty trivial, right? But if you add a unitary gate to our dynamics, now we also basically add an additional layer of computation that you have to perform. Now there is more than one path to each of the final eigenstates, right? You can see that in order to reach 0, you can travel through 1 to 0, or you can travel through 0 to 0, right? So there are 2 paths. And in order to recover the actual final amplitudes, you have to sum over those paths. You multiply this number with this number. That's how you construct the amplitude for this path. You construct the same amplitude by multiplying amplitudes along the edges for the second path and then sum them over. So that's how basically, in this simple example, this Feynman sum works of computing amplitudes for each final state when you have the dynamics. It's kind of similar to who is familiar with neural networks and how the linear layers work in there. It's like basically like a weight matrix. You just apply it to the input vector to get the new weights for the output vector. So it's like a weight matrix of a linear layer in the neural network, right? But now we want to do the same kind of formulation, but again using the same kind of formalism that we used above with phase space and real amplitudes instead of complex ones. And we can also add a measurement for a good measure into the same thing and apply the same transformation that we did before, but to this whole circuit, right? And there's a nice function that will visualize it immediately, right? So we can immediately see what's going on, right? We had an original layer of positive states, which is just our representation of states in this positive basis. So that's why our edges are red. So red just means positive amplitude, blue means negative one, right? So the original state is always positive. It's just the thickness of the edge corresponds to how big is the amplitude for this particular state. But the transition, this is like this transition, this weight matrix from this layer to this one corresponds to this unitary gate that we are applying. Right? That's where you have the negative weights, where you have the edges with the negative weights and negative probabilities of transitioning from one state to another. Right? So now it's again the same kind of formulation in terms of multiplying matrices. Yes, sorry, is there a question? I guess not. Anyway, so yeah. So we have just a multiplication in terms of matrices, again, just a multiplication by this quasi-stochastic matrix for both for the unitary one and for the measurement, right? Those are where the thickness, the thickening comes from the reduction in dimensionality when you perform the measurement. But the point is that it's still then, if you sum over all the paths across this, some paths going to be positive, some paths going to be negative. For example, if you like, pick the top path, like from 1 to T4 to T4 to 1, it only goes from red edges, which are all positive. So you multiply them together, you get the positive amplitude for the whole path, right? But if you pick another path that goes for a negative edge, for a single negative edge, like maybe this one, right, to the same final state, this goes for from T1 to T4 is a negative weighted edge, so it introduces the negative sign to the whole path. So this contribution now destructively interferes with the previous path. So when you're gonna sum them over all possible paths, that's how we get all the destructive interference without worrying about waves and complex amplitudes. You only have the only thing that really contributes to this effect is just the fact that you have two different signs for all your amplitudes for every path, right? So you either can have a positive or negative path, and that's why they destructively interfere. That's how all the quantum effects are coming from. That's the that's the only thing you have to understand at this point. That's how the quantum Feynman sum path, not Feynman integral, Feynman sum works for the simple finite dimensional cases, right? Okay. Okay, at this point, maybe any questions? Because now there's we're gonna try to understand what it actually means in more detail again. We're going deeper. Okay, all right. Okay, so this problem. Okay, again, we have because we have this negative quasi-probability table, which goes from this second layer to the third one. How do you actually interpret it? Right, we can't interpret it as a stochastic process because it's not stochastic because of those negative numbers. So what it actually does, so we can't really simulate it. The only problem with this approach is that we usually think of a physical system as being in a certain state and they evolve, right? Maybe stochastically we're okay with having non-determinism in our dynamics. It's just as soon as the non-determinism can be expressed by some probability transitions. Okay, this state can transition to this state in this multiple ways, in that number of multiple ways, so that we can normalize it and assign some probability. We kind of okay with non-determinism, but we're not okay when it's like this whole transition is represented by this quasi-stochastic process, because we don't know how to simulate it by just sampling new state from a previous state by using some table that you can just read out our probabilities from. Because if you read out the row that says we have to resample this state by negative probability, we have no idea what to do. So in that sense, it's not a computationally constructive process, right? There is no clear way of constructing this dynamics in some way, maybe in some rewriting way, and so forth. So this is like another way of, but at least there's some intuition about how we can think of it first, right? The most basic intuition that you can assign to this quasi-probability tables is this, right? I'm gonna, it's a comes as a word is the inference. I'm gonna explain later what does it mean. First, I'm gonna explain just just like computationally what you have to do in order to think of it in these terms. So again, we have this. We're just trying to explain. Just focus on this particular transition, this particular table, conditional probability table, which is also called quasi bistochastic matrix. Sometimes it's called doubly stochastic. It is doubly because again, it's like sums up to 1 for both rows and columns. If it was only summing columns to 1, then it's going to be just stochastic. But this is like goes in both ways. That's why it's bistochastic, right? So we're going to extract this matrix directly, right? This is Q. We're going to call this matrix Q, and also transform our original state, our probability vector, which is always just a positive probabilities. That's how we present the initial state. So, and the point and the goal here is just to explain what does it mean to multiply this quasi-stochastic matrix with our state, right? So we guarantee that it's going to produce a probability vector, but the way it produces it, it's not clear constructively, right? It's okay that we express it as a just multiplication, but it's not like as a simulation, it's not clear what to do, right? So this is the same kind of amplitudes if you just apply in the usual way. That's how a quantum framework works. Just apply quantum operator to a state, it produces a new quantum state, right? And you can transform it to the same phase space representation and get the same result, right? So we're gonna try to, but here it's just more down under the hood computation. Just multiply a matrix by a vector by a matrix, right? And the very obvious thing to do here is like, okay, you want to get rid of those negative numbers because you don't know how to interpret them. And the obvious way to do is just do some kind of decomposition when you can get rid of it, right? And the most obvious part is that this decomposition, which is like simply called forward-backward stochastic decomposition, which is like expressed our original matrix Q by a product of two matrices, but one of the stochastic matrices, but one of them has to be the inverse. So we have a forward and backward matrices which has to be positive and stochastic, so that we have interpretation for them as a simple conditional probability tables. But one of them, which is the backwards one, has to be inverted. And the backwards one also has a very simple form, just like a mixture, probabilistic mixture of identity matrix, which basically, and a constant matrix, which you can think of it as a, with probability beta, don't do anything. It's just an identity. It doesn't like acts as a process. And with the inverse of probability, just introduce a noise. This is just like a output of probability table with a constant weight, which is just noise, like a white noise for this finite dimensional system. And this is just me directly doing it. That's you just take your matrix Q, find the most negative number by finding the minimal, right? And compute this beta probability, which is guaranteed to be always less than 1 and positive because this is going to be negative, right? So that the denominator is going to be greater than 1. And that's how we compute this forward and backward matrices, right? From beta, and backward one is just gonna be, it's gonna depend on one number, right? So all the computation, most of the computation for this quantum process is related to the forward one, but the backward only depends on a single number. And that's how we can recover it. So basically, we decomposed our original quasi-stochastic matrix as the product of these ones, where F1 is here, right? It looks like a conditional probability table because it doesn't have any negative numbers anymore. And we also normalized it so that it sums up to 1, right? Both columns and rows sums up to 1. So it's a bistochastic matrix, no problem. Yeah, and okay, and the backwards one is also the same kind of, has the same exact properties. It sums up to 1 normalized. Both rows and columns are normalized, but the thing is for the original decomposition has to invokes the inverse of that. So that's the problem. So the only thing we have to explain now, we kind of reduced our problem from explaining arbitrary quasi-stochastic matrices only in terms of one, and also single parameter ones that only depends on a single probability in this mixture, right? So we just this inverse process. And there's like a lot of things you can say about interpretation of that. I'm not gonna like go into detail, but it's like all related to some because the way I called it forward and backwards is already has some relationship to very known interpretations and theories. Like for example, in electrodynamics, there's a Wolfram absorber theory, which talks about all those retarded and advanced ways of propagating signals from sources to absorbers, and the fact that you have backwards and forward traveling ways, you have to like that's the thing that interferes destructively, very similar to the picture we have here, but those are like is done for electrodynamics, so it's much more complicated than this. And there's a advanced inspired by this Wolfram theory, there's the whole interpretation for the quantum mechanics, when all of this is also interpreted, the transactional interpretation, which all of this forward and backwards transitions are interpreted as an actual like retrocausal interaction between states. Like there's a two vector reformulation of quantum theory when you have past and future states influencing each other and all of that. There's like there's a notion in the probability theory, just stochastic matrices, and there's a forward and backward equations you have to construct. There's like all of those theories are somehow very related to this simple picture when we just constructed for a single qubit. Right? Those are these four are for the continuous ones. Right? Those are what you're most likely to find in literature, more information how to actually what those mean. But for finite dimensional system, there's like much less information what it actually how to interpret this. This is a finite dimensional ones, right? Finite discrete dimensional systems. And for those ones, like the matrix we just had, the interpretation is maybe much clearer, at least in theory, should be much clearer. For example, the most basic way in probability theory, if you ask someone, what does it mean to have a inverse stochastic, inverse conditional probability table or something like that, someone would say that, okay, that's just the Bayesian theorem. That's like a default way of applying your conditional probability table in reverse. Or another way of saying it is performing probabilistic stochastic inference. That's why I called it inference. So that's the interpretation for this application of inverse stochastic matrix. It's just performing some inference because you're doing it because you want to construct a state which in the future that influence your past. So it's a kind of, you have to inverse this causal action. So in a way, the quantum process involves both time directions. I'm kind of hand waving here, trying to explain because I'm not sure how to explain it nicely, but this is intuition. It has to involve forward and backwards causal interactions. So, and this is more concretely, this forward and backward matrices say exactly that. In order to inverse your influence from the future, this retrocausal influence, you have to perform the retrocausal process, you have to perform the inference. And that's how you can do it by applying some Bayesian rule iteration. You just apply the Bayesian rule multiple times to some completely uniform prior, for instance, until it converges to the actual future state that you observe by just applying the inverse, right? Or this is also equivalent to some optimization techniques, like just maximizing some particular probability vector in order to reach that vector that we recover by just multiplying this by this, right? So that's the vector we want to recover, which is just QP, which was Q was our original quasi-probabilistic matrix, but we want even though this application we know how to recover just classically stochastically, but applying the inverse that contains negative numbers, it's not clear, even though it's like a very simple matrix and has some it even has some nice geometric interpretation what it does. But the point is here that how we can interpret this part of just applying this inverse of a stochastic matrix. We performing inference, we're doing optimization, we like applying some. This is like something new that I learned just recently. Another way of thinking about this. The Newman series and the Newman algorithm is just one way of inverting the matrix because it's just a more direct way of inverting it using Monte Carlo techniques. And that's kind of exactly what we want. right? We have an inverse matrix, and we want to model this inversion using some computational algorithm or simulation that would be performed with some computational system, right? That's why it's relevant. And this is just one example, just for concreteness. What do I mean, for example, by applying the Bayesian rule iteratively until you reach the same state, right? You can already see that this is how you construct it. You just nest over some prior. You can start with a completely uniform prior, which is just a noise, which is all the states with equal probability. You construct using this prior some Bayesian map, and you apply it to this initial vector, right? And you do it like many times. If you apply it like 10 times, you're not quite gonna reach it, but it converges. So the more times you apply it, the closer you get to the target. So, so what does it mean? Like all this inference, retrocausality, and all backward processes and all that. Does it? It essentially means that we somehow have to give up our frequentist representation of probabilities, because all of this, in order to simulate our backwards processes, we have to somehow manipulate our probability vectors directly. So when we had just a stochastic processes, we still had a hope that we can just invoke some kind of counting algorithm, like maybe we had a multi-way system, right? Everybody knows what it is already at this point. I hope if you had some arbitrary multi-way system for some computational multi-way graph for some computational system, you can think of it just stochastically, because every transition in that multi-way system is just counting of edges. So you can construct the adjacency matrix, normalize it, and you get a Markov matrix. You basically have a Markov chain this way. So on its own, multi-way system doesn't scream quantum theory at all. You just apply simulate your computational system directly, and if you just want to make some probabilistic arguments about like how probable is that particular state when you do a random walk on this multi-way system, how probable it is, you just perform some stochastic process, right? Which is the Markov process. But here we can't really do that, because it's clearly that the direct interpretation of the quantum theory, even for this simple finite dimensional cases, it's not enough. We have to at some point manipulate probabilities directly. Like here we were manipulating the prior, like we were starting from the vector that is uniform, and we were modifying it multiple times until it actually becomes the probabilities that we want, right? But it's not a simulation process as we would do for this forward process. Forward process can be simulated directly by just sampling with probabilities, but this inverse one has to invoke some kind of manipulation of probabilities direct, or some clever techniques. And that's what I hope to, maybe some of you can figure it out, because I'm still struggling with a nice view, nice interpretation of how to do it, right? Maybe someone can take this kind of project of interpreting this process in a more computational way. Maybe there's some ideas here would be, because I've seen some papers about simulating likelihood estimation in a chemical reaction systems. So it's basically just come up with a bunch of reactions, a bunch of chemical formulas from like ingredients of your reactants to the product, and they have some different rates. You kind of can simulate the likelihood estimation, so that the products gonna naturally, after applying this process multiple times, some products and their concentration gonna reach the your estimation, which would be exactly the same vector essentially that you want. But you sampled it, because you're sampling it. At the end, you kind of get it computation in this way. But you have to invoke the idea that it has to be some kind of situation of something, and that's a problem. So essentially, as soon as you think of the system that always being in a single state, it's hard to interpret it as some kind of statistical ensemble of many states, and you're just changing the concentrations of them to represent probability this way. In this way, you can, in a way, this is like one approach to interpreting these quasi probabilities. You can think of a quantum state as actually being an ensemble. If you want to think of hypergraph terms, for example, you can think of it quantum state being a hypergraph very big one, so that you can perform some statistics, and for example, maybe motif counting. Okay, maybe this motif happens in this hypergraph with this frequency, this motif happens with this frequency, so that you can assign some kind of probability distribution to these motifs to a hypergraph, and you can say, okay, this is the quantum state, right? So it represents, so you have some statistical ensemble of motifs, and that's what the thing you evolve. And that's, in that way, if you manipulate these considerations, you can think of them as actually manipulating probabilities directly. So this is one approach, but it's maybe a simple approach, but I don't personally like it because of that. I want some more direct representation with the actual state that we talk about. Like, okay, there's a particle having spin up or having this particular phase point, right? Like maybe this coordinate, this position and this momentum, spin up, spin down in this basis. I want to actually have just a single motif or a single representation in the actual computational substrate or something for that, instead of just a large one, a statistically significant one. So that's why I kind of can move forward from this point. Maybe you have some questions to ask at this point, maybe, because I can we can go in more deeper than that from this point. So any questions? Because I want to go a little bit deeper, like explore that, but in more detail, that positive transformation that I was talking before. So that's a good time to ask questions now. Okay. If there's no questions, let's see. I want to just explore this positive transformation that we had before, which I just briefly mentioned. Right, because we have this problem with negative probabilities, and we kind of can. I mentioned that we can just solve it simply by introducing you doubling the number of your eigenstates or phase points, I guess, and more directly. If in phase space you have some points that can be occupied with some probabilities, and if you want to get rid of negative probabilities, just double the number of points. And if you happen to have negative probability, you interpret it as being in just a different position in phase space. You just assign it a negative sign, right? So we kind of double the number of phase points. And that's what we're gonna do and see what happens, right? So, you can do the same kind of path integral for the discrete systems formulations in that kind of view, when all number of states are doubled, and we have to each phase point we can assign positive or negative sign, and this way you can represent the path summation without any negatively weighted edges anymore. Like you get rid of all the negative transitions, you pushed away all the negativity into states now, all these blue sectors. Those are the things that contain negative probabilities now, not the edges of the transition and the conditional probability tables above. So it's a completely different view. The problem here, the first problem, which is kind of already obvious here, is that if you do it naively, you get the conditional probability table doesn't have to be, you no longer interpret it as probabilities. They are some kind of weights, right? For example, it's like you just, the final, each slice, each state here, to actually recover the original probabilities, you have to subtract the weight for the positive one and the corresponding negative ones. Like, for example, this sector, like bottom left sector, the negative and positive sign has to be subtracted one from each other to recover the original probability. So that's why you're also losing the uniqueness. That's why it's like you can assign different kind of weights, and you can assign different kind of weights as long as there is a difference recovers the original probability, right? So we have multiple ways of doing it. And also, if you do it naively, like this phase space transformation, again, the same kind of transition phase, the same kind of quantum process, random quantum process we were looking into. In this positive representation, it would look like this. Essentially the same kind of numbers, but we turned all the negative numbers into positive ones. It's nothing fancy, right? We doubled the amount of states that our phase space can occupy, but now we have positive and negative states, and all the negative probabilities we just assign to the negative side, to the negative phase spaces. So right, but while doing that, without any normalization, so that we're gonna lose all the original normalization of our stochastic matrices. So it's a subtle, but it's possible. So now the possible it's that's how you can resolve it. It's essentially like when you're gonna try to sum over rows and columns for this double positive matrix, you're gonna get all the different numbers for each column. So you can't really assign a single number to divide your matrix with, so that you can recover all the properties and call this matrix stochastic, right? But you can do it in a different way. That's why it's actually, by the way, that's why, because they're all positive, that's why the weight and the thickness of those lights increases. So the more processes you apply, the more weight in total you get, because you always multiply by some number greater than 1, because you're not longer normalized to 1. Your normalization increases every time you apply the quantum process, and that's what we want to fix, right? And the way to fix it, what am I going to here? Oh yeah, the first thing to notice here is that there's a simple fix to it, just from the already known facts about quantum gates and quantum computation in general. The first comment here is that we pretty much used a very bad basis, right? We used this tetrahedron basis, which is essentially corresponds to this oriented tetrahedron in our block space, right? The one that aligned with this z-axis with our computational basis, because it's very it's very natural to choose this orientation. But maybe it's not natural because it picks out one of the bases in particular for no reason, right? We want some symmetric one, and there's actually a different way of choosing the basis, because we can choose like this tetrahedron instead, which doesn't singles out one of the axes in this block space, which is kind of just some uniformly oriented one relative to this axis, right? This is the basis that we're going to use. Don't worry about why it's called like this. Only think of it as just a differently oriented tetrahedron and differently oriented bases. But you can do exactly the same thing with that in this basis that we did for the tetrahedron ones above, right? But because of this symmetry, it's going to allow us to basically represent, first of all, every unitary transformation. It's like just a fact from quantum computing and quantum information theory. Every unitary gate can be decomposed into just rotations, right? Euler is just like a double cover and all that. It's like basically you can, if given our hold on, maybe broken because it's like doesn't matter. It's like the fact that you can recover the early angles and what the underlying gate can be decomposed by just 3 rotations, right? By around z, y, z axis, for example, right? And each of those rotations turns out to be, if you do it, and you positively transform each of those rotations individually for arbitrary unitary transformation, you can see that each rotation matrix is normalized, can be normalized because it contains this only a single number. So as soon as you divide the whole rotation matrix by this number, each rotation can be turned into a stochastic one. So in a way, after decomposition, we can represent our original arbitrary unitary transformation, and even those that act on multiple qubits, because it also works for higher dimensional or for gates with high arity, right? We can normalize all rotations here. Just doing that, don't worry. This is where I divided by this number, so that our matrices are now all normalized to 1, right? And you can now you have just a sequence of rotations that we can just replace our original unitary transformation with, so that, but each of those are stochastic, just renormalized to back to 1. And that's how you can essentially guarantee that you, in this particular representations, even the intermediate layers are all classically stochastic, and all negativity really pushed to the states, right? Even the normalization is preserved. This is just a maybe I shouldn't have noticed it. Maybe I should just have skipped this about normalization. Just the point here is that, okay, you can think of this this positive transformation as a way of moving all the negativity into states. That's it, right? We moved it, but you have to then, in order to recover the observed probabilities of measurements and everything like that, you have to perform this destructive interference, basically, so that you, for example, if you stochastically know the probability of reaching this state and this state, which is just the same state with negative and positive signs, you have to subtract those weights to recover and normalize back and recover the original probability. So, so we moved all the problems for processes into states, but we now have to but now instead we have to interpret this destructive interference between two different kind of signed states, positive and negative. All right, and it's kind of you in a way you can do it simply for this a single system like qubit. Maybe you already had some ideas, like for example, you can maybe because I've called them like this negative and positive. Maybe you already had some idea of maybe treating them as some kind of particles and antiparticles. Maybe they just states that, because we were mentioning forward and backwards transitions, maybe those are states that simply travel in a different direction in time or whatever, right? Some crazy interpretations for this, but and you can even imagine that how they can destructively interfere without in the multiway system, for example. You can imagine that if you have this system that, for example, corresponds to this final measurement state with both positive and negative states, eigenstates, you can imagine that this being some kind of computational system that evolves on its own, and your resulting causal graph contains two kind of events, right? Because we want to reduce everything to some kind of counting, perhaps, of events or some kind of combinatorics of paths or whatever. But in order to recover these probabilities, but if you have two kinds of events corresponding to evolution of that state, not evolution, just like being just the representation of that state on its own. If it's if it just jumps around between these eigenstates, positive and negative, in such a way that those weights that we just produce stochastically is exactly corresponds to just counting of events of two types, right? There's some we already even within the hypergraph and Wolfram model types of systems, we already talk about events as destroying and creating tokens. Like hyperage being rewritten is the same as saying the hyperage got removed, destroyed, and there is a new hyperage got created in its place, or maybe multiple of those hyperages being created. So in a way, you can interpret all those different weights having input and output, and as soon as you assign the number of events destroying some particular motif or token a negative sign, and assign positive one to the events that constructed instead, you can just statistically interpret this like just by counting these two types of events by exactly this procedure of subtracting positive from negative. Because as soon as you have a sequence in the causal graph, as soon as you have a time lag separated events that destroy and construct the same token, the same eigenstate that corresponds to this quantum state, it's kind of results in a null event in the end. So any observer trying to accumulate the causal graph for the system, the events that basically what I'm saying, the construction and destruction, construction followed by destruction is basically equal to null. So that's why they annihilate each other. So all you have to worry about and what you actually observe is the bias of positive or construction events over negative ones, and that's what we are guaranteed by this. What might be quantum theory guarantees you that the normalization is going to be greater than one. You have this bias of negative over positive, so they can normalize it to one, and that's what in the computational case, that's how you can interpret it. It's just the abundance of positive or negative. Right? That's one way of interpreting it, but that's at least for a single system. It may work for a single system like this one, when you just have you only have in mind just a single qubit in phase space, in this doubled phase space, that just distracts and constructs some tokens, and you can just prescribe the statistics of those events to the numbers that we have, right? You can, so that's what you can do. But I don't think it works as soon as you can start consider multi-party systems. Like as soon as you have two qubits, you have some belt states, the entanglement between qubits, it kind of starts to break down, I think. At least I don't have a good way of interpreting it. But that's what happens. What happens is as soon as you have a well, I have some ideas, but what happens here is that as soon as you have an entangled state, which represents the correlation between two parts of the system instead, you can do the same kind of thing we did above. You can still construct the probability vector for this joint system, right? This is like how it looks in phase space. In positive space, it's gonna look much more different because you have to consider, you have to realize, that this signs that we just described have to act multiplicatively between two different parts of the system, and it's kind of very difficult to interpret now, because as soon as you have one part of the system, for example, like in the conventional scheme that you have, like with Alice and Bob share two parts of the entangled pair of two particles, each of them evolve independently and locally, and you can see that as soon as after evolution one of them is being assigned a different sign, like becoming negative after some quantum process being acted on it, the fact that they act multiplicatively is a bit weird, because now you also have to consider that when you have both of them negative, because they multiply together to give you a positive result, like 2 -1 times -1 is 1, that means it's a kind of problematic to interpret it as some kind of different direction in time or different kind of events being distracted or constructed, because there is no way, I can't imagine how you can interpret two distraction events as a construction event, right? If you have any ideas about that, please tell me. But basically, that's the problem here, that this multiplicative character probabilities becomes problematic, right? So this negative times negative given positive is hard to interpret as soon as you have, in terms of events or in terms of different direction in time, or some kind of recomputation of that particular system and retrying the construction of the state or anything like that, right? There's maybe like some resolution. I haven't tried it. This is just one idea, because you can. I'm not sure how it works exactly, but one potential solution to that may be, okay, if it's a problem with the correlated systems, maybe we can get rid of the correlation, like at the point of preparation of the state. It's like every time you have a quantum state which is correlated an entangled pair, like a Bell state, every time this correlation state is created, that's where the first branching happens, so to speak. It's like you can decompose, because this is as soon as we represent the Bell state itself as a probability vector, it becomes joint one, so it's not separable. So you can't really represent it as a product of two independent probability vectors, probability distributions, right? But you can decompose it as a mixture. So basically, the idea here is that, okay, this decomposition happens at the preparation of the state itself. So because you can decompose the Bell state as a mixture of separable states with some probabilities of being in one of those, that happens at the preparation step, and then it just proceeds so that each of the parts with that probability kind of it happened already, and then it proceeds for all the quantum processes. All those entangled pairs got separated so that all those no locality effects can be accounted for, because now it's a separable state and they can be independently manipulated, even become negative, and you can kind of reason about them independently because they're separate. So you can apply the same logic as above, whatever your favorite interpretation, in terms of maybe this different kind of events that you have to destructively interfere, or maybe it's like moving backwards and forward in time and somehow destructively interfere and retrying your computation. But now you can apply it locally, because we already decomposed it at the beginning, and maybe there's no problem that those two negative signs have to multiply together so that the whole global state has to be interpreted as a positive moving one instead. So which is kind of problematic for interpretation of that. That's what you have to do. Anyway, I'm gonna like do some. I have a lot of time left. Maybe I have a lot of hand waving also left in me. Maybe trying to reason and trying to interpret this even into more with some more examples. So maybe please ask me some questions at this point, because I'm gonna mumble about some examples of how we can recover the same representation differently. Anyone?
Yeah, I had a quick question, Nick. So we mentioned destructive interference as one of the quantum phenomena. We talk about entanglement as like how we can get that aspect to emerge with probabilistically.
Yeah, it's in the probabilistic sense, entanglement is nothing different than the correlation. So as soon as we have a way to represent the state probabilistically, right? And this is just means that any entangled pair is just a correlation.
Okay,
So
so
okay,
it's the correlation
it's
itself.
just two, yeah. It means just 2 points in the phase space are correlated. So if you have 2 qubits and each of them can be in 4 different points in phase space, it means that an overall joint system, which is we call conventionally entangled, which means that those two four pairs or pair of 4 points in phase space are correlated, right? It's like, for example, if one qubit is in that state, in one of the 4 states, then the second qubit is more probable being in this state. So that basically means what? The correlation between them.
Makes sense.
Yeah.
Um,
That's just a
and
argument.
I think just a kind of like a more general question. Whenever you mention quasi-probabilities, a lot of people that study quantum kind of get a bit squirmish. Is there a reason for that? Is it historical?
Really? Did they screenshot? Well, maybe they're just not familiar with that. It depends who you ask. I know that quantum optics is. I already said it, that it's a continuous system, or maybe it's some kind of truncated one. Like if it's usually in the quantum optics systems, you consider some Fock space, which is just a counting of photons, right? But it's usually like an infinite state. It's an infinite dimensional state, but usually truncated to some finite number of states. And you can compute and even some approximations of Wigner distributions. You can just solve some integrals or just do it on the computer. But it's a natural to represent it as a quasi-distribution instead of having density matrices. It's natural to represent quantum states for optical system as just Wigner distributions. I don't know.
I think there was some association with negative probabilities and some historic studies of quantum mechanics that was maybe not like conventional. But yeah, I prefer the version. I like it.
It's not conventional, but it's equivalent. It's not like it's just a mathematical reformulation, right? It's easily, yeah. Conventionally, it was done first for the continuous systems for some reason, because maybe quantum mechanics, it's much easier to reason about quantum mechanics. So it was done conventionally using integrals and Wigner distribution, right? Even there, you can do the same kind of technique of making your distribution positive, but you will lose some other properties, right? There's other kinds of distributions which is still called quasi, like Husimi Q-function, for example. That's a positive quasi-distribution. So it's actually looks like this distribution like this in tetrahedron basis. That's exactly equivalent representation for continuous systems, but it loses some properties of okay, you can longer treat the phase space for this Husimi function as being some coordinate momentum space. It somehow you have to change the quadrature variables or whatever to some other variables. It's like also equivalent here geometrically. It's like we have to change our basic eigenstates, like 0, 1, spin up, spin down to these 4 points of a tetrahedron. You have to change your view of variables in a way, and maybe that's kind of makes people squeamish because
Okay.
you no longer can reason probabilistically about a particle as having a particular position and momentum, because if you want to have this property, you have to consider quasi-distribution, right? Something that we did before in the beginning with negative number, but as soon as you turn it into positive, you have to, your variables become like a combination of position and momentum, right? Some kind of different quadrature, like a sum and difference. those variables can be then thought of as purely stochastically, as long as you're okay with it. Yes. All right. I was going to say, like, I already mentioned that some kind of counting event formulation is possible for at least for a single qubit, maybe with some side notes how to do the same counting argument when you do multipartite systems, right? This is just me trying to come up with simple examples, just representations of in the usual WPP kind of approach using graphs and rewriting rules. This is me just trying to, as soon as you have a causal graph, right, with 2 kind of events, like A transforms to B, B transforms to A, this is like reverse of each other. I mean, like maybe this particular one doesn't have any quantum properties because there is no bias over one event over another. If you just count all the events, they always go 50-50. But basically what it means from the above representation, as soon as you have a causal graph, when you can have can prescribe two events and its inverse, just compute some statistics over those and count both inverse and the forward direction of events, and you have more forward moving ones than backward moving ones, you can kind of look at this causal graph as a quantum state. That's kind of the intuition here. It's like you have a system, like some arbitrary multiway systems, that just performs a random walk on the multiway system, just transitioning from one state to another. While this transition is happening, you're knitting together the causal graph. Maybe there are not just time-like separated events like here, maybe there are more space-like separated ones, but basically you have some causal graph produced as a result of a single path for the multiway system. And if you do the statistics of events, of particular events that you can consider one of them as being inverse of each other, and you find this bias of positive over negative ones, forward over backward ones, you can do this in reverse. You can assign this probability vector to it, right? Because it's just a frequentist representation of probabilities by doing this counting and combinatorics. You can assign a quantum state, and therefore you can do the same kind of transformation backwards and assign a density matrix, and you can do and reconstruct your Hilbert space in this way. So that's kind of the idea here. I haven't, so maybe that's a cool project to have, just to find this some minimal computational systems that have this property. And I already had this. I already did some rulology even without considering hypergraphs. Some more complicated. I just did the rulology for simple elementary CAs, not elementary CAs, but reversible ones and second order. And why is that? Is that those are that looks. We had a nice stream about it like a few months ago, so you can check it out later. But just it's like produces a very nice pictures like this. But the point was the intuition why I did this rulology of finding particular rules. I was searching for the rules exactly with this kind of property, so that this reversible second order CAs, they work in the following way. You have like a usual CA, which is this bottom part. It's just given 3 cells above, you produce a new cell, right? But second order means you also have you also look back one additional step backwards, right? You also look at one cell 2 rows back, right? And you also double the amount of them because you can have this second this additional cell 2 steps back, either black or white, and that's how you can explicitly make your NECA reversible. As soon as you assign black and white, you can basically interpret this black and white second order step as a forward and backward, right? Because they reverse of each other. So that's how you reverse your arbitrary elementary CA by just looking back one additional row, right? That's how you can have an explicit types of events just for simple CA that you can consider forward and backward moving in time because they reverse of each other, and then the color of the cell tells you explicitly which direction you're moving. So it makes it even easier, right? If it's, for example, if it's black, then it moves forward. If it's white, it moves backwards. And what you have to do is just to find such rules that have this bias over positive over negative. And I did this simple experiment. I found like this rule. There are like 2 of them, nice ones. Maybe just 2, maybe more. It depends what kind of additional constraints you assign to them. But like this rule, essentially, if you start with a very large abundance of positive states, that's the only condition, right? Your initial state has to already, to some large degree, move forward. So if you interpret the white cells as a moving forward ones, if you start with like 90% of moving forward cells and you run the evolution, you kind of saturate above 50-50 degrees. So you have this bias. So in a way, every intermediate state here has this bias, so that you can say that overall, the whole cellular automaton moving forward in time, because there's just more black cells than white cells, even though the computation only moving forward. So you have 2 notions of time. You have a computational time, which is just your usual cellular automaton rule application, your rewriting of cells. But you also can assign like an observable time that's counting events, black and white cells, as a different notion, right? Because that's like makes sense, because it's like laws of physics are reversible. So as soon as you have this reversible CA with this bias, you can have similar arguments to that we did above. We can do the statistics and prescribe to every state of the cellular automaton some kind of quantum state, right? Because of this bias, and you can normalize it to 1. The normalization is possible because of this abundance of black cells over white cells. So that's kind of a type of experiments one can do. For example, the types of rulology experiments one can perform for looking for this kind of systems. And why it's important. Another point I want to make is that this kind of counting of events is very similar to what we have. There's like a notion of a very elementary observer theory. There's like many ways you can approach the notion of observer. That's why it's kind of this view I call elementary one. It's like maybe not the best one, but at least very educational one. That how you can teach special relativity in a finite dimensional in any kind of way. This is basically an elementary observer in any causal graph. It's just a path, just a trajectory, time-like separated sequence of events, right? That's what I would call an elementary observer, which you can find and in any computational system, right? You can extract it from the causal graph directly. But the point is that when you have this notion of observers, you can ask such questions. Okay, what would that observer if there's some actual computational system living in that chain, and this represents its internal time, so to speak, right? What kind of other events in that causal graph it can observe and quantify, right? It's all about quantification of that observer of other events. So in a way, you can straighten out this observer chain and see what kind of events it can projecting on that chain, right? Which I mean by is like which events are seen you can project into and out from, right? You can see from the past and the future. Basically, it's like an observer sending a radar signal to the event, and it bounces back, right? This is like you can teach special relativity. It's called Bondi calculus. In these terms, you can check it out. You can express all the special relativistic properties and effects and mathematics in terms of just signal observers sending signals and just waiting for its return, right? Basically, the redshift, computing the redshift instead of a gamma factor in special relativity, you can replace it with this factor instead. And you can and this is just more natural way of doing it for finite dimensional systems. When you just have, instead of a Minkowski space-time, you have just an arbitrary causal graph, and you identify arbitrary observer as a chain. You can quantify all the other events that are observed by that chain. You can assign some coordinates to it so that you can assign x and t coordinates to all other events, because you can consider this is like a 1+1 dimensional space-time. You can consider multiple chains so that you can quantify them like a you can quantify it with multiple chains so that you can assign some access. So that's how we can quantify it with more dimensions, right? But the most important part is that all boils down to just counting of events, right? You're not doing anything particularly interesting, right? As soon as you have this chains of observers, you can ask questions. Okay, given this chain, if you now consider this chain as a particle instead, you can ask some question. Okay, given some other chains that you consider an observer, what kind of how many events are projected on that observer? What's the difference? What's the sum? And you can, there's a natural arguments you can make so that that's how you would compute an like an energy or distribution of energy for that particular particles by just computing statistics of how this particle is observed by other chains. So right, so this is like a very simple example. You can compute energy, momentum, even mass for any chain, like in this just by counting and performing statistics. Then the natural question, why you can't do the same kind of thing with quantum probabilities and all other degrees of freedom you can imagine in quantum mechanics, like spin and so on, by just and all the even the interpretation of probabilities themselves is also boils down to some counting arguments, and that's kind of and that's basically the message I'm trying to make here. It's like maybe the simplest way of explaining all the physical properties, but all boil down on just a measurement and counting of events, even the probabilities ones. It's just the problem is the again the problem with probabilities is again is the negative probabilities. We haven't really solved this problem, but I guess maybe there's some hints. Maybe I managed to convince you that there's something in something there in these approaches, so that you can continue this exploration on your own. And I guess at this point I think I'm finished. Now we can. That's exactly an hour and a half like Xerxes wanted. So I warmed you up for the Stevens keynote. I hope.
We can take one or two more questions if there are, and then of course we can continue the part that you are about to do tomorrow.
Yeah, tomorrow it would be just a more less metaphysical arguments, just more computation. So if you that's like this talk was about you to maybe prepare, make some seeds into and some ideas so that you can like salivate in it for a day and maybe come up with some good questions tomorrow. So that maybe, yeah, I don't know.
I had a quick question.
Sure.
So, say entanglement entropy, right? So we could calculate the density matrix and get out the entanglement entropy. Is there a way to, with the counting argument, is there a way to say count in any way that it'll actually match the entanglement entropy that we get with the density matrix?
There's a no, it's a bit unnatural. It is possible. It's going to be very natural. The more natural way of computing something about probability vectors here would be, of course, the Shannon entropy instead. It turns out that when you compute just the Shannon entropy of these probability vectors, it's not going to be it's not going to directly correspond to one name on one, but it's going to be, for example, it's not going to be this constant value for all the pure states. Like for one Newman entropy for pure states, basically 1, right?
Right.
But the Shannon entropy for those probability vectors kind of slightly differ for pure states, but they're still going to be bounded, so they have a nice interpretation. So in a way, more natural measure of purity for in this kind of representation is actually just the, how do you call it, the divergence from the uniform distribution in some way. You can, not the divergence, or maybe just the distance. Anyway, just quantify. Okay, let me just try to come up with one example. But we have our state rho, right? It has some entropy associated to it, and we also zero entropy, right? Yeah. The pure states have zero entropy, but
Right.
the probability vectors, then they all gonna have some bound, lower bound of entropy anyway. It's not gonna be zero if you just compute the Shannon entropy, but there is gonna be bounded nevertheless. And the better metric that you can prescribe that is most similar to this entropy is actually just the distance from the uniform vector. It's like if you just subtract the 1,4 and square it and compute the norm, I guess this one is going to be constant for any pure state. Let me actually check that. So if you do quantum space, if I'm not mistaken, this is going to be always the same number. Oh, you're confused. I'm a bit confused. Yeah, in our, for example, this one. In our representation of probabilities, this particular metric kind of acts as an entropy because it's constant for all pure states, right? It's like just a geometric representation. It's just the distance from the center of the block sphere or something like that. You just compute the Euclidean distance. The Euclidean distance from in the block space is still constant.
I see.
So so instead of computing, because one Neumann entropy is kind of the problem with it is because it's a optimal entropy. It's like a maximization of all possible entropies that you can get by trying different observables. So in a way, it's not natural. I don't know. I'm not sure that I answered your question. I'm just.
No, I think this helps. This interpretation of the distance helps.
Yeah.
Thank you.
All right, then maybe we should stop now. Thank you, Nick. Thanks everyone for being here. And in about 25 minutes, we'll log on again for Stephen's keynote lecture. So see you all there. Thank you.
Till then.
Thank you.
Thank you.